So hello students. So in this session, we'll see a few selected problems from integration. Okay. So you have, some of you had few doubts on integration. I'll just solve some of them out here. As you selected problems. Let me take up the first one, which is integral 2x over 1 plus x power 4 dx. Okay. So see, there are various techniques, right, in integration. Like you can use substitution method, and then you can use this UV method and so on. So in this, what we can do is, first of all, we'll see how to go about making or converting into a form which is integrable. Yes, that integrand function should be converted to a form which is like familiar to us. So what I can do is out here, I'll just change the font because my question, I can rewrite it as 2x dx over 1 plus, I can write x power 4. Now x power 4, using the laws of indices, it is x power 4 is x square, the whole square, isn't it? So I can write this as x square, the whole square. And now we can use substitution in this case. Put x square is equal to t. Differentiating both sides, we get 2x dx is equal to dt, isn't it? And we have that. If you look here, see, 2x dx is dt. So we have already that function in the integrand. So 2x dx is dt over 1 plus x square is what? T, isn't it? And t square. So if you go back to your standard integrals, you can see that integral of dx over 1 plus x square is tan inverse x, isn't it? Since it's indefinite integration, you'll have a constant of integration as well. So we have here integral dx over 1 plus x square is tan inverse x. Yes. So tan inverse x. So dt by 1 plus t square is tan inverse t. But then you need to back substitute, isn't it? It will be tan inverse. What is t? Tan inverse of t would be, what is that substitution? X square is t, isn't it? So t will be x square plus c. C is the constant, yeah, of integration, indefinite integration. So we have to put in that. Yeah. So there's nothing big out here. It's only that you have 2x dx. So this, when you see, for this you need to know differentiation. When we did differentiation, we have seen that d by dx of x square is what? D by dx of x square is 2x, isn't it? So that's why. So d of x square is 2x dx. Okay, I hope up till here it's been clear to you. We have used substitution and then we have integrated. So you need to know your rules of differentiation well. Yeah, d by dx of what is x power n? D by dx of x power n is n into x power n minus 1, isn't it? So in differentiation, you're not getting any constant of integration, but differential of a constant is 0. That you need to remember. Okay, so let's move on. All right, the next question that we have out here is integral x cube e to the power x square dx. Integral x cube e to the power x square dx. Yeah. So yeah. Again, the only constant out here is e, and of course 3 and 2, the powers. So how do we go about doing this? E to the power x square is an exponential function. X cube is a polynomial function, right? If you go with ilate or liate, so remember, your exponential function will always come after your algebraic functions, right? Or polynomial functions. That means whatever you do, you will have to take this as u. So we have to use the uv form. Why? Because the product of two different things, isn't it? Two different types of functions. So u, and this is dv, like v. So the second one becomes your v. So whatever it is, just have to remember this, that integral of u dv is, what is that? It is uv minus integral of v du. So this is the equation that you need to make use of here. So again, the question is what is u and v, isn't it? So go with Liate or Ilate. It will help you to decide. So okay, it's something like you have your board mass and all, where you decide which operator comes first, right? Same thing here. It will help us to go ahead with this. So what we can do is, again, we have to make use of substitution as well here, for the simple reason that we have e raised to power x square. So now I need to rewrite things in a better way. See the whole trick, or the strategy behind integration is you have to rewrite in a form which is familiar to you. Yeah, standard, to bring it to something similar to a standard form or familiar to a standard form, I would say. And from there you can go. That is the whole strategy out here. Up till then you are kind of lost. Now I can see x square, isn't it? So I can write x square, let's say x square is t. Just trying something. So when x square is t, 2x dx is equal to dt. Okay. So how do I kind of fit in these things out there? All right. So what? So I have x cube. Remember, x cube is x square into x into e to the power x. I'm just rewriting my integrand. If you see, x cube is x square into x e to the power x square dx. Okay, and then I'll apply the dt transformation that I've done here. See, so it will be, so we can write x square, okay, e to the power x square. It's multiplication, right? The order wouldn't matter, into x into dx. See, 2x dx is dt, or if you relate back to this, x dx is dt over 2. X dx is dt over 2. So that's what I'm going to do here now. So this will be dt by 2. So that will be integral x square e to the power x square. Okay, I'll just write in a form that I can understand. So see, x square, isn't it? So in the place of x dx dt. So I'm going to write x square as t. That's my substitution, isn't it? See, go back, relate all the way back here. And e to the power x square is t. X dx is dt. And now I can apply the UV method, yeah? And remember to back substitute for t. So I'll proceed with this. Integral of t into e to the power dt. So integral of t into e to the power t dt. Yes. So t e to the power t dt. It's something like integral of u dv. This is e to the power dt is dv. So let's say u is equal to t, and your e to the power dt is equal to dv. So you just have to integrate both sides. And this, of course, we know this function. Differentiate e to the power t, you get e to the power t with respect to t. And you integrate e to the power t with respect to t, you would get e to the power t. So no change. Simple. E to the power t is equal to v. So now that I have figured out what's my v, so what is the form here? It is in the form integral of u dv, isn't it? We discussed u dv. So what is u dv? It's uv minus integral of v du. Just put in those values here. So going back to u is equal to t. So what is du? Du is dt. So that would give me, what is uv? What is ut? V is what? E to the power t, uv minus integral of v du. V is e to the power t, du is dt. Yes. And now this is a simple function. There's nothing out here. So t into e to the power t minus integral of e to the power dt is simply e to the power t. So I should not stop at this, because I can take e to the power t common, and I'm left inside with t minus 1. And still it's not over, because go back and see what's the substitution. T is x square, isn't it? So that is e to the power x square into t is x square minus 1 plus c. Do not forget your constant of integration because this is indefinite integration. So we have used integral of u dv is uv minus integral of v uv minus integral of v du. We have made use of that here. Yeah, and again Lie8 has been used. So we understood that t is u and e to the power t dt is dv. So going by this, we have this so far. Okay, let's move on to the next problem. So the next problem that we have here is integral of root tan x. Okay, so root of tan x upon sin x into cos x dx. It's interesting. See, now you can do this in different ways actually. So the thing that I would go about, or what comes to my mind, is using the basic trigonometric identities. What I would do is in the denominator of the integrand, look at multiplying numerator and denominator by cos x. This is what strikes me. So let me see what I can do out here. I have in the denominator, yeah, in the denominator you have what? Sin x cos x, isn't it? So it's all about how you are going to align. I told you, realign your integrand to a form which is familiar to you, and again you can proceed from there. So sin x into cos x, I have this in the denominator, isn't it? So what I would do is I'll multiply I'll multiply and divide by cos x. So this gives me what? This part will be tan x. See, multiplying and dividing by the same non-zero quantity doesn't change the value of the expression, isn't it? So sin x by cos x is our tan x. Yes, it is our tan x. I'm trying to do something which I can make my integrand familiar to you in a form which is familiar to you. So cos x into cos x is cos square. Sometimes you might think, why are we messing up like this and why are we converting this? But we are converting it to ensure that we get into a suitable form which we know. So now it's not really substitution that I'm going to do out here. Maybe I will use it here. And it's not a udv because all of them are trigonometric functions. Even otherwise, even if they are functions of the same nature, sometimes we might have to use uv form. That we'll see those later. For now, this is what I'm done to my denominator, isn't it? So now look at the integrand, root tan x. Let me leave it as root tan x. Yes. So I would just leave it as root tan x. Sin x and cos x, sin x into cos x. So that sin x cos x is rewritten as tan x into cos square x dx. So this cos square x in the denominator, when I shift it up, in the sense it becomes 1 by cos square x, isn't it? So what is 1 by cos square x? It is secant square x. Yes, 1 over cos square x is secant square x. So that's what I'm going to do out here. Now, you see, let's have a look. So it's root tan x. Okay. All right. I'll just so 1 by cos square is secant square x dx and my tan x remains down. Let me just keep it there as it is, no change. So what is root a upon a? It would be root a upon root a into root a, which will be 1 over root a. You can relate to this. So this becomes, so tan x in the denominator, I write it as root tan x into root tan x, isn't it? So it gives me what? Secant square x dx over root tan x. And now you see what happens now. So root tan x. So this would be integral of secant square x dx over root of tan x. Now what you can do is put tan x is equal to t. Okay. Now we are going to use substitution. So what happens when you use tan x is equal to c? Differentiate both sides. Secant square x divide dx of tan x is secant square x, isn't it? Secant square x dx is equal to dt. Yes. So, and that's what I have in the, you look at the integrand now, the modified integrand, I have that, isn't it? the numerator. So integral of secant square dx is dt upon what is tan x t, no? Root of tan x is root of t. What is integral of 1 over root x dx? Standard integrals. Yes. So maybe I can, just put 2 into dx by 2 root x, isn't it? 1 over 2 into integral of dx by root x. And this I know is what? 2 into this root x. Yes. Because what is d by dx of root x? 1 over 2 root x, isn't it? So we need to take it from the differentiation, and that's how we arrive at this. So going by this, what am I going to do is I'm just going to rewrite it in that form. That's simply 2 into integral of dt over 1 over 2 root t. That's 2 times of root t. That's 2 into what is root t? Root of tan x, 2 into root of tan x. And of course, don't forget your constant of integration plus c. Yes, so we started off with this root tan x. I modified it now because I know there's a connection between tan and secant, isn't it? D by dx of tan x is secant square x, and that's how I chanced upon this. That I felt this method is suitable. So wherein I can use substitution later on, because this is a way d by dx of tan x is secant square x. So that's how I got to this. So, and then we use substitution, simple substitution, and then we use that integral of 1 over 2 root x dx is root 2 root x. That is d by dx of root x is 1 over 2 root x. And not to forget your constant of integration, which is c. Let's move on to the next one. Okay, the next thing that we have is integral of dx over x minus x cube. That will be integral of dx over x into 1 minus x square. See, I'm just factorizing my denominator. Okay. See, I have, if you have a close look here, x minus x cube. What is it? It is x into 1 minus x square, isn't it? So that would be x into 1 plus x into, 1 is, of course, you have the liberty of writing 1 as 1 square. So a square minus b square is a plus b into a minus b. So I will write this as dx upon x into 1 plus x. So now I am going to apply knowledge of partial fractions, so that I'm able to rewrite this in a form which is familiar to me as a upon x plus b upon 1 plus x plus c upon 1 minus x. And this entire thing is converted to into dx. So I've just written that product as sum here. That's all. Yeah, that is converting it to partial fractions. So this is another technique. I'm going to show you this using this problem. We're going to revise that partial fractions technique here. Yes, we have seen partial fractions earlier. So a upon x plus b upon 1 plus x plus c upon 1 minus x. Yes, I'm just going to tackle this integrand now. So it looks like, why have I messed up so much and brought it to this form? Yes, we do need this because we have to make, or we have to convert, as I said, an integrand into a form which is familiar to us. So moving on, I'll say, so 1 over, so what was that? It is 1 over x into 1 plus x, yeah. So 1 over x minus x cube is nothing but 1 over x into 1 plus x into 1 minus x, which is equal to, just change the font so that I can relate to this. Now you see, I'll write it in red. It's a by x plus b upon, so plus b upon 1 plus x plus c upon 1 minus x. Yes. So, and now I will have to take charge of this. So to find a, See, the denominator of in A we have x, isn't it? So equate x to 0. We have to find the value of A here. Yes, I need to find the value of A, isn't it? So if I have to find the value of this A here, so equate x to 0. What's the denominator of A? X, isn't it? Equate that x to 0. So A by x I have, isn't it? So when you make x is equal to 0 in that expression, forget A upon x now, yeah? So when you put, what happens? B over 1 plus x, yeah? So you get 1 plus x plus c into 1 minus x. So what I will do is I'll just show it in the form which is relatable. Just here. So when you take this in this form, 1 over x into 1 plus x into 1 minus x. Yeah. And you take LCM, it's going to be the same thing here, x into 1 plus x into 1 minus x. So A into, if you use LCM, A into 1 plus x into 1 minus x plus B into, so what will be that? It will be B into 1 minus x into x plus C into 1 plus x into x. Yes. So you can cancel out the denominators both sides, leaving me with 1 is equal to A into 1 plus x into 1 minus x. Of course, that's nothing but 1 minus xy, but we'll just write it down. B into 1 minus x into x plus C into 1 plus x into x. So we are solving by partial fractions. Yeah. So now what I can do is I can put x is 0, isn't it? Because that's the denominator of your A. By doing so, what will I get? I will get the value of A, coefficient A, isn't it? So put x is 0. What happens? 1 is equal to A into 1 plus 0 into 1 minus 0. See, what happens to B? 1 minus 0 into 0. So B into 0 and C into 1 plus x into 0, right? So you're going to get 0 into 0. So that's again 0. So 1 is equal to A into 1 plus 0 is 1. Yes. Into 1 minus 0 is also 1. Giving me what? So this is 0, 0, that's gone, isn't it? Anything into 0. So A into 1 is A. 1 into 1 is 1. A into 1 is A. So A is equal to 1. Yes, I got my value of coefficient A. Okay. So now in this expression now, again, let's go on to, so you got A is equal to 1, isn't it? In this expression, that is this expression. This expression, what did I do? I put A is, x is equal to 0. That, because to determine A, I need to equate the denominator of A, that is x is equal to 0. And that's how I got this, yes. Now I'll just solve for B and C in a similar manner. Okay, so now what is the coefficient to find B? To find B, what we can do is now the coefficient of the denominator of B is 1 plus x. No, when you equate that to 0, we get 1 plus x is equal to 0 or x is equal to minus 1, isn't it? So in the expression, I put an expression in the box, right? The equation rather, I'll put x is equal to minus 1 so that my A gets knocked out, isn't it? 1 plus x, 1 plus minus 1 is 0, isn't it? So it becomes 1 plus minus 1 is 0. So a into 0. So it's gone. B into, I'm putting x as what? I'm putting x as minus 1. So b into 1 minus of minus 1, that is plus 1, because x is minus 1, isn't it? Into minus 1 here. So if you see here, see, if you follow the pointer, in the place of x, I put minus 1. Again, here I put minus 1. Yeah. So minus of minus 1 is plus. And of course, c again gets knocked out because c 1 plus minus 1 is 0 into x. Again, that is 0. So a and c get knocked out, leaving me with 1 is equal to b into, so what is that? 1 is equal to b into 1 plus 1 is 2 into minus 1. Minus 2b is 1. So this means minus 2 into b. So minus 2b is equal to 1. Yeah. Or b is equal to minus half. B is equal to minus 1 upon 2. Okay. So b is equal, minus 2b is 1, or b is equal to minus 1 upon 2. So we have come up till here. Yes, let's put that also in the box. So b is equal to what? Negative half, isn't it? So we'll require all this. See, it looks lengthy, but this is the procedure that we need to follow for formulating the integrator in that manner. Okay, so next we have to tackle for C. So now the coefficient of the denominator, rather, the right word is denominator of C is 1 minus x, right? When you equate that to 0, you get x is equal to 1. So to find C, you have to make 1 minus x equal to 0, or 1 is equal to x, isn't it? Taking x to the other side, or x is equal to 1. So put x is equal to 1. So in the expression in the box, in the equation in the box, you get a is equal to 1 into 1 plus x into 1 minus 1 is 0. So a gets knocked out. B. So what happens to b? B is again 1 minus x, 1 minus 1 into 0 into whatever. So it gets knocked out. So c into x is 1, no? 1 plus 1 into 1. Yes. So that would be, so a into 0 is 0, b into 0 is 0, 1 is equal to c into 1 plus 1 is 2 into 1. So c is equal, so 2c is 1, or c is equal to half. C is equal to half. So we'll put that as well there. So c is equal to half. Let me just put in that value. C is equal to 1 upon 2. Yeah. Now go a little back and see what's there in my integrand now. Integrand was 1 over x minus x cube, isn't it? See this one, I'm just putting a highlighter there in yellow. You can see there, isn't it? This was my integrand, right? And I wrote it in this form. And then a by 1 by a by x plus b by 1 plus x plus c by 1 minus x. Yeah. So we'll have to go with that now. Okay. So integrand becomes a by x plus b by, what was that? B by 1 plus x, isn't it? Plus c by 1 minus x dx. And what's our a? It's 1 over x. A is 1. B is minus half. That gives me 1 over 1 by 2 into 1 plus x, because b is 1 over, b is negative half, right? And c is 1 upon 2 into 1 minus x dx. So now we have a very important result, a formula. One integral of 1 over x dx is log x, base e is implied, or you can even say ln x. Yes. So this tells me that it's to the base e. So now I can use that, isn't it? So that would be integral of 1 by x dx minus half into integral of dx over 1 plus x plus 1 by 2 integral of ds over 1 minus x. So integral of 1 over x dx is ln x minus half into, instead of x you have x plus 1, so it would be ln of x plus 1 plus 1 by 2 into ln of 1 minus x. Yes, you're going to make sure that 1 minus x is going to be a positive number because we're defining only for positive values. Base e is implied, isn't it? That would be ln x minus half into ln of x plus 1 plus half into ln of 1 minus x. So maybe you can we can club all this. You can say ln x minus ln of root of x plus 1, half goes up, right? X plus 1 to the power half is root x plus ln of root of 1 minus x. Now, depending on the method that you have done, you might get different values for integration. You may not get a unique result always. You need to remember that. Okay, so even in the, forget the concept of integration, even otherwise. So now we can use our laws of logarithms, isn't it? Log a plus log b and so on. We can club these two. We get ln of x into root of 1 minus x. Log of a plus log of b is log of a into b minus ln of root of x plus 1. That would be ln x into root of 1 minus x upon log a minus log b is log of a by b. So using that, yeah, and I can, maybe I can write it as ln x into root of 1 minus x by 1 plus x or x plus 1 plus c. Yes, this is the one we need to remember. This, when you differentiate, you would be getting what? When you differentiate, go back, you would be getting that function 1 over x minus x cube, which is the integrand in this case. You can always cross check. See, when you perform your integration and you get your result, when you differentiate, you should get back the integrand. That's when you know that your method is right. And you may not get a unique answer because the methods might vary. In this case, we have used partial fractions to solve this. So the explanation so far has been helpful to you and clear to you.